Thank you, thank you. Thank you. I would like, first of all, to thank indeed the organizer for all this wonderful long meeting where I learned so much and we had so much useful discussion. So my talk will be more philosophical talk, and that's actually I take an opportunity because I will say certain things about homotopy type theory, but I think I will not be obliged to introduce it. I'll give some definitions which I will need, but I will not try to make systematic introduction, which already was made several times during this meeting. So I will begin with the critique of Ernst Cassirer in 1907, his critique of Russell's Principles of Mathematics, 1903. So I'll consider short argument which concerns that question of mathematical objects. Then I'll try to explain his argument and try to make sense of it and try to show that it's really worth be taken into consideration, that it is a serious argument. Then I'll try actually to extend it, talking not on Russell, but rather on Hilbert's axiomatic method, and I will use a relatively recent presentation of Hilbert's axiomatic method made by late Jaakko Hintikka in 2011, and I try to apply the same sort of argument to this Hilbert-like axiomatic approach and axiomatic setting. So I'll try to argue that there is indeed a problem there, which, as I'll try to argue in the second part of my talk, can be solved by using homotopy type theory. So that's the plan. Okay, let's begin with Cassirer. So he provides the following critique. I read it a bit, long quote. So he says, there is a problem that lies wholly outside the scope of logistics, and logistics is just mathematics based on symbolic logic, which according to Russell actually is mathematics. So Russell's strategy is actually to say that logic and mathematics is the same, but that's not absolutely important for that argument, as I'll show later. So what's important, we'll see now, all empirical judgments must respect the limits of experience. That's, of course, part of kind of Kantian orthodoxy, which I'll explain a bit later. Now, what logistics develops, Russell's logistic, is a system of hypothetical assumptions about which we cannot know whether actually established in experience or whether they allow for some immediate or non-immediate concrete application. So his problem, you see, is how that kind of mathematics applies, say, to experience, to natural science. So that's whole worry is not for mathematics alone. That is important. According to Russell, even the general notion of magnitude does not belong to the domain of pure mathematics and logic, but has an empirical element which can be grasped only through essential perception. From the standpoint of logistics, the task of thought ends when it manages to establish strict deductive link between all its constructions and productions. Thus, the worry about laws governing the world of objects is left wholly to the direct observation, which alone within its proper very narrow limits is supposed to tell us whether we find here certain rules or a pure chaos. According to Russell, logic and mathematics deal only with the order of concepts and should not care about the order or disorder of objects. I'll try to explain what he means here. As long as one follows this line of conceptual analysis, the empirical entity always escapes one's rational understanding. The more mathematical deduction demonstrates us its virtue and its power, the less we can understand the crucial role of deduction in the theoretical natural science. That's a problem which became later known by Eugen Wigner as a problem of so-called unreasonable effectiveness of mathematics. Why this deduction, this mathematical structure, ever works in science. You see, and that is an important assumption which I think I just also take after Cassirer that I mentioned that yesterday during this discussion panel on foundations, that I believe after Cassirer that reasonable foundation of mathematics should somehow make effectiveness of mathematics reasonable, right? Actually, Cassirer himself, he has rather radical view in this respect. So he says, actually, he says the next quote, replying to this question, what actually remains, what we can say from Kant's philosophy in 1907. He's very well aware that all this idea that we may rely on Euclidean geometry somehow cannot be no longer sustained, right? So he's very well aware of new developments in mathematics and in physics, and he kind of embraces them, and he makes his methodological principle to learn about very recent science and talk about mathematics and physics, meaning his contemporary research rather than some outdated one. And then he says the following: logical and mathematical concepts must no longer produce instruments for building metaphysical world of thought. Their proper function and proper application is only within the empirical science. So he apparently shares a view that one of my professors, Vladimir Arnold, just bluntly expressed it by saying that mathematics is a part of physics, something like this. And I will not necessarily subscribe unto that view, right? Mathematics may be somehow more involved relationships with physics and natural science, but I think, at least I do think that that is something very essential for mathematics being part of mathematics, being applied, being used in natural science and also in engineering and technology. So that's I also take to be a serious issue, even not subscribing under the thesis that all of mathematics should be necessarily somehow applied. Okay? So now I try to explain what he means by objects and what is really the worry here. So, no, I just took this quote from Galileo that everybody knows, that he says language of nature is somehow mathematics, and mathematics consists of circle, triangles, and blah, blah. But the important thing that I'll spend some time to show is that this traditional geometry, which we find in Euclid and later developments, which I shall later talk only about Euclid, but I think that point did not change in the 17th century. So this kind of deductive order in which this geometry organizes itself, and which we'll see in more details in a minute, it cannot be described as logical order, at least if we logic understand something like rather narrowly and something like in usual sense as an order of certain propositions, right? We take certain propositions as axioms, as assumptions, and we have certain rules of inference, which we call logical rules, right? And we infer some further propositions. So it's not as this traditional geometry is organized. That I'll show a bit later. I'll try to give some evidences for that. But now I just want to say that this different order, which I call constructive order, and here by being constructive, I mean something, I would say, I think more general than usually people mean by talking about constructive. Actually, it's very overloaded term, of course. Constructive, being constructive. In every context, it needs to be specified. But I will talk, in this talk, I'm speaking about being constructive in the sense that being related to object building, to building objects, rather than just propositions. you see? So I rather assume that there are kind of non-propositional objects in our theory, and there are certain rules about these objects, not just, semantics for certain propositions, right? But also certain rules, certain way to organize these objects. We'll see on more concrete examples how it works. And that indeed needs to be contrasted against what we may call probably even today kind of mainstream notion of object, and which Cassirer somehow finds already in Russell, and that I took from relatively recent monograph of Charles Parson on mathematical objects. So he says, okay, you can read, I will not read it, but his idea that he just takes this notion of object, the most general notion of it, from logic. So somehow for him, being an object already means what in logic we may call individual, alternatively, right? So in that sense, I will show in which exact sense it's kind of rather poor notion of object, right? A very primitive, just a thing, something like that, right? And so the claim is that notion of object indeed, first of all, it makes a difference between this formalized mathematics of the 20th century and more traditional mathematics. And what I try to argue, what I try to argue, that this specific notion of object, which I'll show in a minute, is really crucially important for the success that this traditional mathematics in general and traditional geometry in particular had in scientific applications, like in Galileo time. And more specifically, I think it was very crucial for thought experiments, right? For thought experiments. So this is the argument. That indeed, with this formal approach to mathematics of 20th century, so far we're talking about Russell, but I will extend it later, you'll see, to Hilbert formal approach, we lose something important in mathematics, which allows to that, which supports application of mathematics and physics, and more specifically supports thought experimentation, making thought experiments, which, by the way, in this case at least, rather straightforwardly translate into real experiments, because after all, what really counts are not thought experiments, but real experiments in natural science, right? But that feature that I'm talking about, that I clarify exactly, it allows what in today's philosophy of science sometimes is called experimental design, designing experiments, right? And it works first from thought experiments, then through certain designing experimental setting, and after all, performing real experiments. Okay, coming back. So what I'm talking about, we'll consider only very beginning of Euclid's Elements. Here I just quote Jan Müller, who I think is the greatest, scholar, Euclid scholar, recently died, unfortunately. So that is from one of his papers. He says, I know of no logic which accounts for this kind of inference, because of course we do find some sort of inference in Euclid, right? We have first principles, which I'll describe in a minute, and we have something that follows from them. So there is certainly something like deductive structure. But then the question, of course, how we can reconstruct this structure, understand how, in modern terms, how it works. So he says, Jan Müller, that he knows no logic in modern logic, and he's someone who is knowledgeable of modern logic, and he says there is nothing like that would correspond to Euclidean formulation. There in Euclid, one postulates that certain action is permissible and infers the doing of it. He does it. An obvious analog of the procedure is provided by the relation between rules of inference and deduction. So here there is an analog between rules, which we'll see in a minute, are geometrical rules, actually, about geometrical objects, right? How we take certain objects and make up certain other object with them, right? With what's going in logic, we have inference, right? We have certain proposition, make up certain other proposition. Right, and so how it looks like in Euclid, I a little bit simplify. So I take first three postulates, first three common notions, or so-called axioms. If I take the whole picture becomes more complicated and less coherent. So, but at least I think this is still the very much core of what we find in Euclid. So three postulates. First of all, see, they are not propositions, so they are not axioms in modern sense. They don't, how to say, state anything, right? They rather describe, I think rather reasonable interpretation describe them as an operation. Just see, there are kind of input in everything and output. So we input 2 points, right, and we output a line. This is the first postulate. We are given 2 points and we output a line. Second, we are given a line and we output a continuate line. Here it's, we may say, output is not precisely defined, but okay, we leave it. And the third one, we again given a line and we produce a circle with the center of one of ends. I'm sorry, yeah, it's with the non-symmetric out of this line. So those are rules, okay? And then we have so-called axioms, which look like propositions, just beware all of them involve equality. So it's kind of theory of what does mean to be equal, theory of equality, right? And actually they also work as a rule. I would say, and Jan Müller says the same, is kind of replacement of logical rule, if you like, right? So there is kind of logic here by restricted to identity statement, to equalities. A is equal to B is kind of a standard form of proposition, and basically there is no others. No, at least in this formalized part in Euclid, right? And so this, by the way, in Aristotle, we find this very much looks like, I think I made this right, like perfect syllogism. That was many times remarked as perfect syllogism in Aristotle. So if you say A is B, B is C, then you see here 2 things are equal to the same C's, so they're equal to each other. So there is some similarity to logical principle. And again, you see, there is no axioms in the modern sense at all. So something similar to, like simple assumptions. Things like this, they rather follow from definition. For example, we have definition of circle, which says that all radii are equal, and that can be used in proofs of theorems. But postulates and common notions, they are rules. And rules of 2 different sorts. Postulates are specific rules, say, for geometrical objects, and common notion, they more general rules, which apply both not only in geometry but also in arithmetics, right? And which basically rules about equality. You see, which I think, no, it's longer discussion, I will not develop it, which kind of replace properly logical axioms. And there is nothing like properly logical axioms. Of course, you may always read it into and add, but there is no, how to say, natural way to do that, actually. Right, so that's more or less how it works in Euclid. Yeah, and then Jan Müller describes actually this Euclidean derivation, then he says, is a thought experiment of a certain kind, an experiment intended to show either that a certain operation can be performed, as in so-called problems. The thing is that this, in modern edition, you find propositions in Euclid. Proposition 1, proposition 2. In original text, even, there is no even word proposition, something like that. There are You know, these blocks which are just numbered, 1, 2, 3. And, but then there is a long tradition, it's in commentary of Proclus and many others, that actually these blocks are of two different sorts, so-called problems and theorems. And in problems, you need to make a construction. For example, first proposition, so-called, is a problem which says to construct a rectangular triangle, right? And that has the same form as a postulate. You see? So it's kind of, again, operation by giving a side, right? So you are given a line, then you need, that's, how to say, part of your formulation of your problem, make triangle, you apply this postulate twice, you get intersection. Many commentators say that this is not really justified by any principle that they should intersect. But anyway, so then you apply second postulate, so it's P3 twice, then it's P1 twice, okay? And so you get your triangle, but then you need to prove it, right? So, and you prove that you've got what you say you got, right, in the beginning by using this third axiom. Oh, first axiom, by saying that AB is equal to AC by definition of triangle. That's an assumption which just comes from definition. And similarly, CB is equal to CA, and finally they are equal to each other by third axiom. You see, but the whole thing again is a construction. It's nothing is stated here, right? It's a construction, but interestingly, that to perform it, you still need to apply some like proof, some like statement. So here, this propositional part just plays a role inside construction. You see, and in many other cases, it's just the other way around. In case of so-called theorems, for example, the theorem that sides of isosceles angles at the base of isosceles triangle are equal, then it's the other way around. You first make so-called additional, right, auxiliary construction, then there is, which I will not describe, there is reasoning, you prove it. You see? So in both cases, there is construction, there is proof, but in problems, it looks like your proof helps you to make your construction, and in theorem, it's just the other way around. Construction helps to make your proof. But actually, it's this, they have, I don't have now time to develop all that, but both problems and theorem, they have exactly the same structure, which, I say it again, it's not easy to grasp by usual logical means. I think exactly for that reason that Jan Müller stresses, that most of modern reconstruction, they just begin with this assumption that everything is a proposition from the beginning. And that's, I think, you can do that and, make this exercise, but then it's has really little with Euclid as it is in our original. Okay? No, so just repeating quickly this point, the claim is, I think, that this character of being, okay, me say, thought experiment, if you like, it's crucially important for scientific application. Of course, I have no time. I think that's something to be further developed, discussed, but I think it's really, how to say, the core of modern science to being experimental, of course, right? And what it allows to be both mathematical and experimental, and that particular character of, say, traditional mathematics. Okay? Now that's, I say, claim that I probably cannot fully justify during that talk, but I think it sounds plausible, right? And perhaps we may discuss it later. Okay? Okay, no, just coming briefly back to Cassirer. So finally, in the nutshell, his argument is this, that Russell's logic comprises only rules applicable to propositions, so it's logical deduction in narrow sense of being logical, not in Kantian sense, by the way of being, transcendental logic or anything like this. It's in narrow sense of being logical. And then we, in this, setting, we just don't have interesting notion of object, which is needed actually for applying mathematics in science. So that's argument in the nutshell. So idea is that this kind of construction we perform, say, in Euclid by ruler and compass, they actually important for doing science because in that way, we actually make physical models, we produce, by the way, real equipment or real, technical artifacts, so it's not only relevant, of course, for science, but also for technique, very generally, for engineering. That is something very basic, and here we just, in that setting, we lack this feature, and so it kind of. Okay. No, one may argue that's kind of old story, it's interesting, but now I come kind of revive it, and I do think that similar argument applies to Hilbert's approach, even if this Hilbert approach you take to be, semantical, because there are basically two traditions to treat this Hilbert approach, and Hilbert himself, I think, he kind of oscillated between the two. Well, perhaps with some preference. I'm not making historical point now, but at least one way of thinking about Hilbert's approach is, by emphasizing this importance of semantic. And that's what Jaakko Hintikka does. So he says, what is crucial in the axiomatic method is, on the view of the axiomatized theory, is that an overview on the axiomatized theory is to capture all and only the relevant structure as so many models of the axioms. The class of the structure that axioms are calculated to capture can be either given by intuition, freely chosen, or introduced by experience. So the second quote just answers the question where models comes from, right? So, okay, we have some axioms, but where we get models? Well, we know from Hilbert's own examples, we find this somehow in traditional mathematics, right? Arithmetical models, for example, or we use kind of intuitive traditional geometry to cook up some models of not traditional theories, like Euclidean models for some non-Euclidean geometry, this kind of things. But you see, there is no, really method to getting models, right? We say it's intuition, freedom, whatever, right? So the only way to control models is setting up axioms. So we set up axioms. Of course, we may have some intended models, so we have something in view, but then we kind of describe this with axioms. Right. No, okay, I'll come probably miss that point. And so what I think is a problem in this method is the fact that these models are not well controlled actually in that way. Just remember that Jan Müller said, okay, Euclid does something very different. It's thought experiment as opposed to Hilbert's deduction. But Jaakko Hintikka now, he says that that actually it is deduction. Hilbert method is thought experiment, You see, because indeed one may argue that this Hilbert's axiomatic method, axiomatic freedom, so to speak, of freedom to create any axioms we like and find models and derive theorems, that's kind of thought experimentation, right? So in that sense, one may argue that this today received axiomatic method just performs all these thought experiments maybe better than traditional Euclid's geometry. But I do think that Kasirov's argument applies here for the following reason, that this method again, does not give you way to build models. It just requires that you kind of find these models somehow which fit your axioms, right? And claim is that this, if you think at least about models in Tarski spirit as something like through satisfaction relation, right? So the claim is that satisfaction relation just does not give enough control to make up interesting models and moreover models useful in science. And so it's kind of yes-no question game with nature that Hilbert's method provides, right? We put axioms, and sometimes they may turn to be true. Then we are, in fine. So we derive theorem. We can look if the semantics kind of sound, if the theorem is also true, and we may also actually define our logical constants just in a way that would also kind of correspond, which would work well with nature. But problem is that I think that modern science just does not allow kind of direct evaluation of your axioms. It's rather absurd. Every kind of evaluation should be already based on kind of mathematical model, right? And how to build that model. And I don't think that it may be just be given by intuition game. So we need certain principles for building a model, which is not just, goes for a question of evaluating this model with certain theories. They need to be kind of systematically built from simple elements or something like this, right? And of course, we are now talking not about early modern science as in Galileo case, right? We talk about 20th century science. And here, many people would think in beginning of 20th century and first part of 20th century that actually science itself changes, its character in such a way that this Hilbert-style axiomatic becomes appropriate. You see? Exactly because we no longer may rely on this intuitive thinking about, like in Galileo case, like rolling balls and this stuff. In our mathematics, we don't need it either. So we should do something much more abstract. And for example, Patrick Suppes, it was his long life project to axiomatize all knowledge or develop kind of technology of axiomatization which would work in physics, in sociology, and everywhere. He was, by the way, the pioneer of what became today known as knowledge representation in computer science. Right. So his idea was just to use the Tarski-style semantic for everything. And of course, he was aware that the sense in which people talk about models in science is not the same as in model theory, right? But he argued that the difference, after all, is not that big. You may really think about all models in science as just set theoretic models and use it in physics. And also he thought that the specific character of recent science makes it even better than models are no longer, intuitive, no longer directly connected somehow with everyday experience, and have this abstract character, and that would work even better for science, which it didn't, I think, as a matter of fact. And again, I think it's that's I actually added already during Ursa's talk, that because it's even I just mentioned Suppes, but that was already, of course, one of Hilbert's ideas to axiomatize physics. So he says we need to explore somehow all logically possible physical theories, right? That makes part of his description of this task. But my critique is that at least if we understand logical as he understood himself, as we may judge after his work in geometry, right? That is too narrow and may not work. And at least for actually two different reasons. That first, it requires somehow to choose a logical framework in advance without looking on what you are axiomatizing, right? And we may not just have in advance a good logical framework. But second, and I think it's even more serious reason, perhaps more controversial also, that way of controlling models is just too weak. It's not sufficient. If we simply want to, to specify class of models by giving their, axiomatic description, by listing certain propositions which they satisfy, and then we want to choose some finite list of this proposition and generate all the other. But just that way of specifying models by propositions can be too weak and maybe not specify what really needs to be specified in science. So that's so my kind of guess, again, I cannot justify it in full now because it's long talk in philosophy of physics this time. But my guess is that this notion of thought experiment is as much as important in today's science as used to be in early modern science. And perhaps it didn't change its character absolutely radically. And rather the problem is that it's, I think standard picture from quantum mechanics textbook of showing Heisenberg inequality with some very, old-fashioned equipment. So my guess is exactly the problem is the equipment is too old-fashioned. That we really need a better way, a better geometry to, to think about these things, to design these experiments, right? And not in terms of really outdated stuff. So I rather, my suggestion, rather than just saying we don't need anything of that sort, we should really think abstractly and, somehow express all this in terms of abstract set theory, for example, right? Without making any direct connections to what we really observe. Rather find a new, say, setting, kind of geometrical setting, which would allow us to make such things more coherently and more effectively. Okay? Right. That's I just say. So what I kind of looking for, having Euclid is one good example, and trying to, to make up kind of a modern version of it, is a kind of formal framework which support deduction, some form of deduction, meaning you may specify first principle and rules which generate more, and which combine logical rules, which constructive rules, which allow one to build complex construction from primitive construction. Like in Euclid, we may build a lot of things by rule and compass. All right. So that's kind of a setting. And right, and I want to call it constructive. And here actually, I find it in Hilbert Bernays of 1933. They already use here constructive in that sense. So it's not absolutely, my personal use of this term. Okay, and so now I'll try to briefly just to show that homotopy type theory may serve this exactly that purpose, that it may do the job that I just described. Okay. So here I think it's important actually to distinguish, because when we are talking about homotopy type theory, obviously it's we do talk about semantics, right? If we just talking about pure syntax, it's say syntax of Martin-Löf type theory. Right? And talking about semantics, we need actually to distinguish between original semantics given by, that's escaped by Martin-Löf himself in his 1983. I think Thorsten referred to the same book or maybe it was someone else, but in 84. I think it's the same book, but just different editions. All right? So it's one thing what Martin Löw, what was his intended semantic at that point, and what we have with HoTT. And I think that's, of course, correct to say that HoTT provides some sort of refinement of this original semantic. But it also quite correct to say that, strictly speaking, they are different. They are incompatible. You cannot you cannot just preserve this in full. So this refinement is not fully conservative, put it that way. All right? And this refinement, which is relevant to my talk now, it's refinement notion of proposition. Because to begin with, Martin Löw just provided kind of 4 different interpretations, semantic interpretation of types, of what does it mean of term to be of certain type, right? It's a basic form of judgment, 1 of 4, right? So he provides 4 interpretation about which he does not think as actually alternative. Rather, his strategy is somehow for saying it's all the same thing after all. Also, not only on formal level, but also on kind of conceptual level, that he says that after all we should identify concept of set with that of proposition. That, of course, goes along with this Curry-Horvath, all this kind of motivation, right? So here, and this applies universally to types. So that's, he says, about every type whatsoever in this system, okay? Every term, you may think about term of type as element of set. Of course, it's not Zermelo-Fraenkel set, right? It's rather constructive set. You may also think about as a proof of corresponding proposition or method of realizing intention or expectation, or method of solving the problem. It's all kind of the same. And what we get with HoTT, okay, I will not explain, I think it's already know. I think this is this hierarchy, which Martin Löw was not aware of. Yeah. And I think about this hierarchy. That may be a controversial point, and I would be interested to get some objections, perhaps. But I do think that this homotopical hierarchy it's really robust structure, which belongs, in a sense, to pure syntax, which is there, right? So you cannot say it's just one more way to think about these types and their terms, right? Just add to this Martin Löw's list, let it be type a space and term be a point. No, just using these geometrical ideas, real mathematical advance is discovery of this stratification, right? Which is purely formal property. If you don't like geometry, you may not think about this in stratification in geometrical terms. You may describe it absolutely formally, but it's still there, right? No, then, of course, you may argue that it's semantically irrelevant, but I think it would be a really weird idea. So if you making semantics of your, syntactic system, you somehow, your semantic, I think, should reflect important formal features, all right? And this is, again, it's a formal feature, as far as I see, right? And for that reasons, we really should refine this original semantics, and it's refined, as already many times discussed during these days, by saying that actually it's what in HoTT book is called mere proposition, right? It's minus one type, which, by the way, Martin Löw in this 93 book, he rejects this notion of proposition just as truth value as classical. He, for strong philosophical reasons, he does not want this to be called a proposition. He says proposition somehow is given through its proof, and he wants this notion of judgment be more fundamental than that of proposition. So unless you have an element, so a proof, you don't have really a proposition, and that on that basis he says it's more or less the same as constructive set. But here we actually recover quite classical notion of proposition. Then, of course, we recover sets, again, not quite Frankel sets. And here we recover notion of, I would call theorem, right? It's something like proposition, but that time it has an explicit, not just truth value, but particular proof, put it that way, right? It could be called a theorem or perhaps problem and methods, particular methods solving the problem. And more generally, of course, so we've got this hierarchy, right? And higher types, higher proposition type, I would just call, say, objects, okay, by analogy, geometrical objects, and construction. Here is a little bit subtle point, but it has an analogy again in traditional geometry, because officially we may say, okay, types are spaces and objects are points. So concept of object and that something is simple. But then, of course, we may have something like constructions. So we may have, no, it's kind of a fragment of this groupoid structure on whichever level. No, if I just say first level, I may have, I don't know, two objects and two different paths between them. Something like this, right? So that would be construction. And this notion of construction is kind of, how to say, it doesn't have precise identity condition. But I think the same thing we find in Euclid. Because if we say object is something given by definition, like triangle, right? But that would be wrong to say, and that's a crucial point about Euclid, emphasized by Kant, among others, that geometry does not operate just with this thing. Crucial is when I may make further constructions, say, continue this side, for example, right, make parallel line and prove theorem about internal angles, you see? So it's somehow not just an object, but objects that I may kind of develop, add more things, and similarly we have here, I think, right? And actually analogy is quite precise also in the sense that these points are just subject of definitional identity, judgmental identity, you see? So it's exactly what given by definition, and so-called construction is what we prove further, making further propositional identity claims, like making this further paths, you see? So that's kind of way of thinking that suggests itself. Now, of course, it's important to have in mind that the difference between Euclid and, say, modern geometry is that in Euclid, actually, there is no properly concept of space at all, right, arguably. At least there is, except, I say, there is interesting thing that, of course, you have plane geometry in that book, right? And in the last three books, you have stereometry, 3D geometry, right? And it is used, very non-trivial fact, that if you, in 3D geometry, you have a plane as a kind of basic form, right? Basic type, you have a plane. But then, of course, Euclid very strongly uses the fact that on this particular object, you have the full plane geometry. It's living there. On every plane, we apply everything you proved. So you see, there is this, how to say, in a sense, he understands that in particular objects may work as a universe, as a space, I would say, right? No, in today's geometry, of course, it's just for saying that notion of space is not just kind of scene or vehicle. We construct stuff with spaces, we given two space, we construct new space, and so on. So that's, of course, is assumed here. No, here maybe I skip for just saving time because James Ladyman, who just exposed yesterday, he has some objections against thinking about terms as objects, which I think are not very defendable. Okay, so I probably skip all this part. So what I think really very important in HoTT is this fact that we have propositions as just one layer of types, kind of lower layer of types, among others, right? And rules of HoTT or Martin-Löf, they apply actually cross types. So if we have, for example, we have given types A, B, we may form, is a special case, actually normally a rule is more general for P, but I just write for constant function type, right? So when A, B are of -1 H level, right? So they are propositions, that of course is implication. And for high level, this is a map space. It's a space of maps from A to B. So we have the same rule, which works for proposition as, you may say, logical rule in narrow sense of being logical, and works for spaces and objects in these spaces as constructive rule, like postulate in Euclid. Like you have 2 points, you construct a line, you have 2 spaces, you construct map space, and you specify a special space. So in that sense, I qualify it also as a constructive theory, right? And now how to use it for physical experiments? No, just for finishing, I have one example. I try to analyze this Frege's morning star, evening star example, right? So if you have 2 objects like that, say 2 points given through their definition, and then if you want to say that morning star is equal to evening star, so you choose some type, which, I don't know, type of celestial object. So that is a new type, right, which is type of pass from one to another. And finally, what you do, you somehow observe one or reconstruct one path, which just gives you the required proof that this is the same object, right? This is classical situation. And but thing is that I think if you begin to think in kind of, say, you have again 2 objects, but here you have double slit, right? It's kind of natural again to say that with double slit, right, you have one homotopy type, that of circle, as one, and if you either remove the slit or you just you shut down one of the slits, right, then it comes back to the point type. So you have this different. No, it's not unlike Urs's work. I think it's just intuitive picture, but I do think that at least that kind of geometry may perhaps with some more specific set of, I don't know, intuitions, may be useful for making experimental design, say, for in quantum physics, just like Euclidean geometry supports experimental design, say, in early modern physics. Yes, that basically the same. That's it, and I have some papers and a website where you can find more. Thank you very much. Yeah.
Thank you very much. Joanna?
Hello, thank you for this nice talk. But at some point you talked about outdated methods. I assume you meant set theory or something similar?
No,
okay.
no.
Just wanted to... Anyway, what I wanted to say is that this foundation of mathematics also should also produce results in the foundations themselves and analyze these foundations, right? And the ability, for example, of set theory to code objects in unexpected ways, like code the formulas and stuff, and then build models inside the models and reflect, is something to this direction. How would homotopy type theory maybe fare in this direction?
No, I think there are people who may answer better than me, but my understanding is that model theory of homotopy type theory is there were some interesting talks, but it's not something yet, say, to the point, right? But it's what's important to my argument is that already, I think, we don't have actually good and universally accepted notion of model. Because from your talk, right, that became clear that Tarski notion of model just is not sufficient, obviously not. Because on the one hand, it's just too weak. You see, it works only on propositional level, and but if we kind of automatically apply it on all this homotopy level, it's kind of too weak. We need really stronger properties, something like being initial object in an appropriate category. You see, so but my central my argument, I didn't discuss that, is that at least in homotopy type theory, we have this, non-propositional interpretations, and we have propositional interpretation, right, as a part of the whole thing. I think it's may correspond to what, for example, von Neumann wanted when in 1932, right, he wrote Mathematical Foundation of Quantum Mechanics and first came up with this idea of quantum logic. Was later paper with Birkhoff, just of logic making part of bigger mathematical setting. And that's, I think, what, at least formally by its properties that we already know, homotopy type theory may provide, right? And that other systems just don't. Yes.
Yeah.
Mm-hmm.
Hi. So I could imagine a rule of stereometric geometry which says that if you have a plane and a figure, you may project the figure to the plane. Something like that.
You may figure, you mean three-dimensional?
Shape. Yeah, three-dimensional shape. I may project its shadow onto the plane. That would be a construction that is not reversible. And so I wonder, you say that points should be objects and the paths between them should be constructions, but that would imply constructions are invertible. So do you think that homotopy type theory goes far enough in taking this view that in a sense higher equalities between terms of a type are constructions?
Do you ask about reversibility? That's the point, huh?
Yeah. Not all constructions being reversible.
Oh, yeah. No, I think no. I think in existing homotopy type theory, everything is reversible, right?
Right.
All right. Yeah, that, by the way, was one of the talks. I forgot, shameful the name of the speaker. He's not here. Who provided this up and down paths? Right. No, I do. No, at least formally, it's clear, right, that there is a lot of research which is not used in existing homotopy type theory, and which concerns exactly the fact that paths are naturally directed, and while in homotopy type theory, as today, we just formally reverse them, and that's we lose. No, in a sense, it's good. Maybe lose certain structure that it just makes things simpler, but I think it's a big resource.
Can I comment? So I think you're confusing the notion of construction with the notion of proof of equality. So a construction is like a function. It might well not be reversible in the sense of having an inverse. A proof of equality is something, which has a symmetry and you can reverse it. They're different things.
I was referring specifically to the claim made in the talk that objects should be considered as points of a space and paths between them as types of constructions. So.
No, frankly, my use of notion construction is rather loose, as well as in Euclid, right? So I would call. No, I just use. Perhaps I should find another word because in object is something given by definition, right? And we need something more, like in Euclid, right? So triangle is object and a circle is object, but what really essential for doing geometry is the fact that we may kind of extend them. And these extended things, which are maybe not subject on any kind of well-formed predicates, right? But so I try to use construction in similar sense. Perhaps another word should be taken, right?
Bas Peters?
So, I mean, the question you asked, isn't it, I mean, it's something that has been discussed a lot on the, I mean, both in Princeton and also later on the mailing list. So for topos theory, this is something that can be done, and in this way it can be argued that topos theory, or as a constructive higher order logic or a constructive set theory, I mean, you can actually do most of these constructions that you're used to in set theory, and it's actually, so you can build a syntax in there. So we would really like to do the same thing for homotopy type theory, but for similar reasons. And people have been trying to encode the syntax of type theory directly into homotopy type theory. And it's more or less clear how it should be done, but no one has fully completed the construction. Mike Schulman has worked very hard on this, and he has a long blog post called Type Theory Should Eat Itself. And so this is really what one wants to do also for, I mean, for ordinary type theory, but also for homotopy type theory. And the interesting thing is that there's a whole class of very interesting problems connected to semi-simplicial types, and a number of the definition of an infinity category in homotopy type theory, and also the initiality conjecture. So there's a whole class of problems that people have worked very hard on, and the interesting thing is they seem to be very closely connected. So people have been proposing new systems like the HTS system that was also mentioned by Vladimir in the first lecture. So we have a good feel about what's going on, but this hasn't been completely solved yet. So it's a very interesting question.
I just wanted to ask about your model in the physical world, your idea of that. Yeah, so I mean, the morning star I could think of as being in the type of celestial bodies, but also in the type of maybe all bodies. But somehow intuitively it's really the same thing. So I feel like it's more in line with regular set theory where elements can be members of different sets. So I wonder if you think this is like an advantage or a disadvantage, or if you have any.
Look, perhaps it actually was part of James Lederman's objection, which I just skipped, because his objection against thinking of terms of types as objects is exactly that. I would say a lack of sufficient polymorphism, right? So every type is of particular type and not of. But my impression is it can be improved. Some more polymorphism can be added. And in many contexts, by the way, we just don't need much. We need much polymorphism than we usually, assume in kind of metaphysical talk. Exactly in Euclidean proofs, when we kind of pick up particular triangles, we don't need it to be of any specific sort. We don't need it to be isosceles. It's a kind of general triangle, right? There is a whole work of so-called arbitrarily objects by Kit Fine. So I do think that it's not, fatal objection in the sense that there's more polymorphism may be somehow regulated.
There was the last question in the first row.
I wanted to ask a question about the relation to physics or to experiment. And well, now we have an example of old physics, and you had one slide where you stated, new physics needs new constructive geometry, and I do not want to doubt that geometry provides a lot of elucidations how physical theories work, but if you actually want to relate to experiment, then somehow, then even in physics from 40 years ago, then non-commutative geometry won't help much, but then you need, then physicists have to calculate their path integrals or whatever and do their renormalization, and then very different problems start, and mathematical physics gets really precarious about how to deal with that. And and as long as you stay in some pre-quantum geometric conceptions, you will not you will not directly help the calculations for LHC or whatever. And
I'm not sure I really correctly understood, but no, okay, you'll interrupt me if I'm replying different question, but this is big issue, of course, I can discuss, which in particular was discussed between Bohr and Einstein, right? And so Bohr's point was that you cannot do anything, in quantum mechanics properly after the model of classical physics for the following reason, that all your experimental design is inevitably classical, and our kind of perception and conception of object is classical, and we should use all that for have some glimpse.
I'm actually more pointing to the later developments. I think things you mentioned for Neumann, he kind of settled the question of classical quantum mechanics that can be done properly mathematically, but for all quantum field theory, which has been done since the 50s, it's not clear at all, and all these geometric stuff kind of remains on one side of the problems which occur there, I think, and maybe one should. Maybe it's just to point at some problem where there actually, I don't know, maybe there's where it's difficult to see what might give some great breakthrough, or where there are actually very big problems.
No, what actually happened with this von Neumann approach, that it was very severely criticized by logicians. You see, so this idea to develop logic as a part of physics was really very, rejected, and by the way, Supes and other people. And the argument was, no, of course they would object, is nothing like axiomatic. He would claim in this book von Neumann that is axiomatic development of quantum mechanics. They would say it's nothing, it doesn't fit the modern standard of being axiomatic at all, no, which is true, of course. But they would also argue that the following, that since in quantum mechanics all mathematics is classical, and classic mathematical is based on classical logic, then we just shouldn't go for this quantum logic, or we may somehow play with this, but
maybe just in one sentence.
So maybe,
I think,
sorry to interrupt, maybe we can postpone the discussion for later, and we would now thank the speaker again.
Thanks.